Hello there, and welcome to our second video on proportional reasoning. In this one, we're going to be looking at representing rates pictorially. So pictorially basically means we're going to be looking at some different graphs. So on our graphs, usually we're going to have some different lines. So we're going to first review some stuff that you would have seen from a previous math class dealing with slopes. So there's going to be some different slopes that are going to be important. So you could have a line that points upwards like this one. That is what we call a positive slope. You could have a line that points downwards. There's no example down here, but if you had one pointing down, that is negative slope. Zero slope, this is when you're going to have a flat line. So this one here, that's going to be zero slope. And then undefined slope, that is when you have a line that is actually just pointing straight vertical. So now that we've done that little review, let's look at our first question. And all of these questions, if you want to pause the video and try to guess or figure out what the answer is for each one, you're welcome to do that. So it says, in which of the following graphs is the runner running the fastest? So in order to figure out which one is running the fastest, we're going to have to look at what's on the axes of our graph. So I'm going to zoom into this one here first, graph A, and I can see on my axes I have time, it's measured in seconds, and then on the vertical axis it says distance from the starting line, and it's measured in meters. So this change in the y, in the vertical, that is the change in your distance from the starting line. So if you went from 20 to 40, right, we went up from 20 up to 40. The difference between 20 and 40, that would be 20 meters. And then this is our time. So from time 0 all the way over to 4, that's 4 seconds. So in 20 meters, that took us 4 seconds to get there. So if I were to simplify 20 meters divided by 4 seconds, that's going to give me 5, and this is meters per second. Make sure you always have your units on there because that'll tell you what the slope represents. So in this case, the slope, this is 5 meters per second. So that is the speed. So I figured out how fast that one's going. Now I just got to calculate the other one. So let's move to B here next. So that one went from a distance of 0 all the way up to, that's 30. So we went 30 meters, so let's write that, 30 meters, divide by, and then our time, again, it went from 0 to 4, so it took us 4 seconds. And if we take 30 meters and divide by 4 seconds, you're going to get 7.5, so that's 7.5 meters per second. And I might not have mentioned why we're taking the one number and dividing by the other number. That's because this right here, that is what we call the rise. You will have done that in a previous math class, hopefully. And then this amount that we moved over, that is called the run. And our slope is the rise over the run. So maybe I'll just write that. Slope, this is our rise over our run. We're going to see that later in this lesson as well. So B is now done. I'm going to move over to C, and that one just has a flat line. So we started at the 40 meter mark. We are a distance of 40 meters from the starting line, and we just stayed there the whole time. As time is moving forward, we just stayed at the 40 meter mark. So our change in distance, we actually went 0 meters. We didn't go up or down, and that took us 4 seconds. So if you go 0 divided by 4, that's going to be 0. So we got 0 meters per second. So that one, they're not moving very fast. They're not moving at all. The last one, part D, this one they went from 20 all the way up to 30. So we went 10 meters. So we moved 10 meters from the starting line. And then that took us again 4 seconds. So this is divided by 4 seconds. And when you divide those, you're going to get 2.5, and again, keep our units, meters per second. So now I can look at all 4 of these, and I can see that this one right here, that one is the fastest, 7.5 meters per second. So our answer for this, we can circle down here. It's going to be graph B. And another reason we can tell that that one is going to be the fastest is because it has the steepest slope. So as long as all of them have the exact same units on the axes, it went 0, 10, 20, 30, 40, 0, 1, 2, 3, 4, and they all have that exact same thing on the axes, Then what you can do is just look at the slope. Whichever has the steepest slope, the steepest pitch, that one is going to be the fastest, regardless if it's pointing up or if it's pointing down. Pointing down would just mean that you're coming back down to your starting position. Moving on to number 2, and you can pause the video if you want and try to guess this one. It says, which of the following graphs indicates that one of the runners started 10 meters ahead of the other? So looking at all the graphs, remember this was the distance from the starting line. So if one runner started at, say, like 0 meters and the other runner started at 10 meters, that right there, they have a 10 meter head start. In this one, 0 to 20, that one they have a 20 meter head start. This one, they're both starting at 0, so they're both starting at the starting line. And then this one, they're both up at 10, so they both have kind of a 10 meter head start. So this is the one, though, where one is starting 10 ahead of the other one. So that is graph A, so we can circle graph A. And again, the reason was because this is 10 meters ahead. Moving to number 3 here now. This one says, in which of the following graphs are both runners moving at the same speed? So remember, we said that the slope represented our speed. So if they have the same speed, that means that they have the same slope. So I just have to look at all of these and find the one that has the exact same slope. So clearly this one right here, they both have the exact same slope. These lines are parallel. So our answer to this one, we can circle graph D. Lastly, we got number 4 here. So it says, which sentence best describes the runner whose distance time graph is shown below? So we're going to read through these options here and pick the one that best describes the runner. Now what you want to do with a question like this is you want to look at what they have on the axes to help determine what this graph is saying. So we are going to read the axes labels to help understand or interpret the graph. So again, we have time on the horizontal axis. Time should always be on the horizontal axis if time is involved. And then we have distance on the vertical axis. So I can see we started at a position of 0 meters from the starting line. That means we're on the starting line. And then as time moves forward, our distance is going up. So we are getting farther from the starting line. Then we get to this point, and then our slope changes. So if our slope changes, you can see from this one, we went 20 meters, and that took 2 seconds. In this one, we went up, that is less than 10, and that one took us another 2 seconds. This is another 2 seconds. So with this one, I traveled less distance. So I didn't go as fast because I traveled less distance in the same amount of time. So because this one is less steep, that means that we are not moving as fast. So let's write that. So we have reduced our speed. So let's read through these options and see which one best describes our runner. So A says the runner ran forward for 2 seconds and then ran backward for 2 more seconds. So we know that can't be the case because I ran away from my starting line. We ran 20 meters away, and then all of a sudden we're here. This is almost about 30 meters away. So we didn't go closer to the starting line. We continued forward and we went further away. We went up still. So A is going to be wrong, so we can cancel that off. B says the runner ran forward for 2 seconds, then stood still for 2 more seconds. So we didn't say that we stopped. We went up till here, and then our distance is still going up, so we're still moving forward. So B can't be the answer either. C says the runner ran forward for 2 seconds and then ran forward more slowly for 2 more seconds. So that kind of matches up more with what we said up here. This slope right here, this had a reduced speed. So that matches what C is saying. So let's just read D just to make sure that C is our choice. D says the runner ran forward for 2 seconds and then turned right and continued forward at the same speed for 2 more seconds. So same speed. This has different slope, so it's not the same speed. So this same speed, that's definitely wrong. So C is going to be our answer. Next, we're going to look a little bit more closely at what slope does. So we're going to be analyzing some different graphs. So it says the slope of a graph represents the rate of change. So rate of change is just how one variable changes with respect to another. It could be like your height for how old you are. It could be how cold something is for the amount of time that's passed. It just depends on what you're dealing with. So slope, you should have seen this before, but we can represent slope a few different ways. So for slope, we normally use the letter M. And to calculate slope, what we do is we take the rise and we divide by the run. That's what we did on that first page. Another way to say this is you just take the change in the y and divide by the change in the x, because the rise, this is up and down, that's what the y deals with, and the run, this is left to right, that's what the x deals with. So we have an example for this. It says, what is the average speed of each runner? So we have a runner A and a runner B. So we're going to find the slope of each of these. So I'm going to have slope, we'll call it slope A, and we're going to use this kind of formula right up here. So the change in the y. So I can see the y went from 10 up to 30. And maybe first I'll just label these. It goes x and then y. So our y went from 10 up to 30. So we went from 10 up to 30. So I'm just going to subtract those two to figure out how much of a change there was. And then our x's went from a 1 to a 3. So I'll subtract those two. 3 minus 1. So 30 minus 10 is going to give me 20. And then 3 minus 1, that gives me 2. And our units for these two numbers, the 10 and the 30, that was 10 meters and 30 meters. So I'm just going to add in here, this is meters. And then for the 2 that we had gotten, that was because we went from the 1, so that was 1, and we went up to the 3, so that was seconds. So I'm just going to put seconds. And if we take 20 meters and divide by 2 seconds, 20 divided by 2, that is 10. So this is 10 meters per second. So that is our speed. That's how fast we're moving. Next, we can do our slope for B. So I got slope sub B, and we're going to do the same kind of thing. So our y's, it went from 4 up to 8. So I'm going to subtract those two, 8 subtract 4. And then our x's, it went from 1.6 to 3.2. So we'll subtract those, 3.2, subtract 1.6. So in the numerator, 8 subtract 4, that's 4. And then in the denominator, 3.2 subtract 1.6, that's 1.6. And if you go 4 divided by 1.6, you're going to get 2.5. And our units are the exact same. This is meters per second. So those are the two average speeds for each of these runners. So if it asks which one's moving faster, the red one, or runner A, is going to be moving faster. You could have told that though, because it's much steeper. So moving to our next example. So this is a one with a family. They're going to be moving. It says Rajesh and Kunal's parents have a 4-door car and a minivan. They are trying to determine which vehicle to take on their move and which vehicle to ship. And then it says both vehicles cost the same amount to ship. So you don't got to worry about one being larger and it costs more to ship. Both cost the same amount to ship. So first thing I'm going to do is I'm just going to label these graphs. That one is, they called vehicle 2. And then this blue line here was vehicle 1, so I'll call that V1. So I want to determine the slope of each graph. So let's do V1 here first. So that is going to be the change in the y's. We went from 48 to 90, so I can take 90 and subtract 48. And then I'll divide by our x's. It went from 800 to 1500. So we got 1500 subtract 800. And then we'll start to simplify this. So 90 minus 48, that is going to give me 42. And then in the denominator, 1500 subtract 800, that is going to give me 700. And now if I take 42 and divide by 700, that is going to give me 0.06. And now our units, the y was liters and then the x was kilometers. And we went y divided by the x's. Remember, slope, it was the change in the y divided by the change in the x. So we're going to take liters and divide by kilometers. So this is liters per kilometer. And then we can do V2. So V2, the y went from 72 to 135. So we can take 135 and then subtract 72. And then our x's went from 800 to 1500. So we'll take 1500 and subtract 800. And in the numerator, when we take 135 and subtract 72, you're going to get 63. And in the denominator, that's the same calculation as before, so we're going to get 700 again. And then when we take 63 and divide that by 700, we're going to get 0.06. 0.09, and then our units again are going to be liters per kilometer. So what we just found, this right here, if you got 0.06 liters for every kilometer, that right there is your efficiency. So that says this right here. It says, as a unit rate, the slope of each graph represents the number of liters of gas used to drive 1 kilometer. This indicates the vehicle's fuel efficiency, and often it's given as liters per 100 kilometers. Oftentimes a vehicle will even have a gauge or a reading that might give you that. So if you ever wanted to convert one of these, I'll just convert this one. If you had 0.09 and that was liters per kilometer, if you wanted to change this into liters per 100 kilometer, we need to get this kilometer right here to be 100. So in order to do that, we would have to multiply by 100, and then we'd have 100 kilometers. But if we do that in the denominator, you'd also have to do that in the numerator. So multiplying that out, if you had 0.09 and you multiply it by 100, that's going to be 9, so that's 9 liters. And then in the denominator, the kilometer times 100, that is 100 kilometers. So that's how you would convert into liters per 100 kilometers. So moving to part B now though, it says vehicle 1 has a fuel tank capacity of 70 liters. How many kilometers can vehicle 1 go on 1 tank of gas? So what we're going to do is we're going to use our information above here where we had V1. So I'm just going to write that out. It was 0.06 and that was liters per kilometer, and that was 1 kilometer. If you want to put the 1 in front there, you could add the 1. And we want to figure out how far you could drive with 70 liters. So what I'm going to do, I'm going to make a proportion, and because liters is in the top here, I'm going to put liters in the top here. And then I got to put the number that went with that, and that was 70. So 70 liters, and this is going to be X amount of kilometers. So this is just a proportion where we can use that cross multiply and divide. So doing that, we're going to get X is equal to, so we'll cross multiply these two. So we got 1 times 70, so 1 times 70, that'll just be 70. And then divide by the number across from the X, which is 0.06. And when we do that, we are going to get 1,166.6 repeating. And then our units, that was kilometers. Part C asks the same question, but now it refers to vehicle 2. So for vehicle 2 up top, that was 0.9 liters per kilometer. So I'm just going to write that down here, 0.09 liters per kilometer. And I'm just going to put a 1 in here. So 1 kilometer. And we want to figure out now if we had a 76 liter tank. So I'm going to have to put 76 liters up in the numerator, again because this had liters in the numerator. We always have to have matching units. And then we can put a X down in the bottom. So to solve for X, it's the same kind of calculation. We're going to cross multiply. So 1 times 76, and then divide by the one across from the X. So that was 0.09. So 0.09 goes in the denominator. And then when I divide those, you're going to get 844.4 repeating. And our units again are kilometers. Part D here next now says which line most likely represents the car and then also the minivan. So if we look at our lines, this blue line here went up. We got to about 1,500 kilometers, so 1,500 kilometers, and that took 90 liters. The other one, we got to 1,500 kilometers, but that took us 135 liters. So that took a lot more fuel. And if you think about cars and minivans, most likely a car is going to get better fuel economy. So we can say that V1, the blue line, is going to be the car, and then the red line, the V2, that is going to be the minivan. And then again, the reason was because the car uses, or should use in most cases, less gas. Lastly, we have part E, and this question says, which vehicle should the family drive to their new city? Justify your answer. So if you were driving, most likely you'd rather drive something that got better fuel economy. So you're most likely going to want to take the car over the van, but there could be options where you might pick the van over the car. So most likely you're going to pick the car because you're going to get better fuel mileage. But if you drive the van, it could be because maybe it has more seats, maybe it has more space to fit things, maybe it was more reliable, better tires, maybe you just prefer it. It just kind of depends. So that was the very last question. Our homework questions are just here at the bottom, so we're on page 450.